In statistics, a mediation model is one that seeks to identify and explicate the mechanism or process that underlies an observed relationship between an independent variable and a dependent variable via the inclusion of a third explanatory variable, known as a mediator variable. Rather than hypothesizing a direct causal relationship between the independent variable and a dependent variable, a mediational model hypothesizes that the independent variable influences the mediator variable, which in turn influences the dependent variable. Thus, the mediator variable serves to clarify the nature of the relationship between the independent and dependent variables. In other words, mediating relationships occur when a third variable plays an important role in governing the relationship between the other two variables. Researchers are now focusing their studies on better understanding known findings. Mediation analyses are employed to understand a known relationship by exploring the underlying mechanism or process by which one variable influences another variable through a mediator. For example, suppose a cause X affects a variable presumably through some intermediate process. In other words, X leads to M leads to Y. Thus, if gender is thought to be the cause of some characteristic, one assumes that other social or biological mechanisms associated with gender can explain how gender-associated differences arise. Such an intervening variable is called a mediator. Barron and Kenny's steps for mediation. Barron and Kenny laid out several requirements that must be met to form a true mediation relationship. They are outlined below using a real-world example. See the diagram above for a visual representation of the overall mediating relationship to be explained. Step 1. Regress the dependent variable on the independent variable. In other words, confirm that the independent variable is a significant predictor of the dependent variable. Independent variable dependent variable. I²11 is significant. Step 2. Regress the mediator on the independent variable. In other words, confirm that the independent variable is a significant predictor of the mediator. If the mediator is not associated with the independent variable, then it could be unregistered trademark T possibly mediate anything. Independent variable mediator. I²21 is significant. Step 3, regress the dependent variable on both the mediator and independent variable. In other words, confirm that the mediator is a significant predictor of the dependent variable, while controlling for the independent variable. This step involves demonstrating that when the mediator and the independent variable are used simultaneously to predict the dependent variable, the previously significant path between the independent and dependent variable is now greatly reduced, if not non-significant. I²32 is significant. I²31 should be smaller in absolute value than the original mediation effect. Example: the following example, drawn from Howell, explains each step of Barron and Kenny unregistered trademark S requirements to understand further how a mediation effect is characterized. Step 1 and Step 2 use simple regression analysis, whereas Step 3 uses multiple regression analyses. Step 1. How you are parented predicts how confident you feel about parenting your own children. How you are parented confidence in own parenting abilities. Step 2. How you are parented predicts your feelings of competence and self-esteem. How you are parented feelings of competence and self-esteem. Step 3. Your feelings of competence and self-esteem predict how confident you feel about parenting your own children, while controlling for how you are parented. Such findings would lead to the conclusion implying that your feelings of competence and self-esteem mediate the relationship between how you are parented and how confident you feel about parenting your own children. Note: if Step 1 does not yield a significant result, one may still have grounds to move to Step 2. Sometimes there is actually a significant relationship between independent and dependent variables, but because of small sample sizes, or other extraneous factors, there could not be enough power to predict the effect that actually exists. Direct versus indirect mediation effects. In the diagram shown above, the indirect effect is the product of path coefficients A and B. The direct effect is the coefficient C. The direct effect measures the extent to which the dependent variable changes when the independent variable increases by 1 unit. In contrast, the indirect effect measures the extent to which the dependent variable changes when the independent variable is held fixed and the mediator variable changes by the amount it would have changed had the independent variable increased by 1 unit. In linear systems, the total effect is equal to the sum of the direct and indirect effects. In nonlinear models, the total effect is not generally equal to the sum of the direct and indirect effects, but to a modified combination of the two. Full versus partial mediation, a mediator variable can either account for all or some of the observed relationship between two variables. Full mediation, maximum evidence for mediation, also called full mediation, would occur if inclusion of the mediation variable drops the relationship between the independent variable and dependent variable to zero. This rarely, if ever, occurs. The most likely event is that C becomes a weaker, yet still significant path with the inclusion of the mediation effect. Partial mediation maintains that the mediating variable accounts for some, but not all, of the relationship between the independent variable and dependent variable. Partial mediation implies that there is not only a significant relationship between the mediator and the dependent variable, but also some direct relationship between the independent and dependent variable. In order for either full or partial mediation to be established, the reduction in variance explained by the independent variable must be significant as determined by one of several tests, such as the Sobel test. The effect of an independent variable on the dependent variable can become non-significant when the mediator is introduced simply because a trivial amount of variance is explained. Thus, it is imperative to show a significant reduction in variance explained by the independent variable before asserting either full or partial mediation. It is possible to have statistically significant indirect effects in the absence of a total effect. This can be explained by the presence of several mediating paths that cancel each other out, and become noticeable when one of the cancelling mediators is controlled for. This implies that the terms partial and full mediation should always be interpreted relative to the set of variables that are present in the model. In all cases, the operation of fixing a variable must be distinguished from that of controlling for a variable, which has been inappropriately used in the literature. The former stands for physically fixing, while the latter stands for conditioning on, adjusting for, or adding to the regression model. The two notions coincide only when all error terms are statistically uncorrelated. When errors are correlated, adjustments must be made to neutralize those correlations before embarking on mediation analyses. Sobel's test. As mentioned above, Sobel unregistered trademark S test is calculated to determine if the relationship between the independent variable and dependent variable has been significantly reduced after inclusion of the mediator variable. In other words, this test assesses whether a mediation effect is significant. Examines the relationship between the independent variable and the dependent variable compared to the relationship between the independent variable and dependent variable including the mediation factor. The Sobel test is more accurate than the Barron and Kenny steps explained above, however it does have low statistical power. As such, large sample sizes are required in order to have sufficient power to detect significant effects. This is because the key assumption of Sobel unregistered trademark S test is the assumption of normality. Because Sobel unregistered trademark S test evaluates a given sample on the normal distribution, small sample sizes and skewness of the sampling distribution can be problematic. Thus, the general rule of thumb as suggested by McKinnon al. is that a sample size of 1,000 is required to detect a small effect, a sample size of 100 is sufficient in detecting a medium effect, and a sample size of 50 is required to detect a large effect. Preacher and Hayes bootstrap method. The bootstrapping method provides some advantages to the Sobel unregistered trademark S test, primarily an increase in power. The Preacher and Hayes bootstrapping method is a non-parametric test. As such, the bootstrap method does not violate assumptions of normality and is therefore recommended for small sample sizes. Bootstrapping involves repeatedly randomly sampling observations with replacement from the dataset to compute the desired statistic in each resample. Over hundreds, or thousands, of Bootstrap resamples provide an approximation of the sampling distribution of the statistic of interest. Hayes offers a macro http www.ofhayes.com/ that calculates bootstrapping directly within SPSS, a computer program used for statistical analyses. This method provides point estimates and confidence intervals by which one can assess the significance or non-significance of a mediation effect. Point estimates reveal the mean over the number of bootstrapped samples, and if zero does not fall between the resulting confidence intervals of the bootstrapping method, one can confidently conclude that there is a significant mediation effect to report. Significance of mediation. As outlined above, there are a few different options one can choose from to evaluate a mediation model. Bootstrapping is becoming the most popular method of testing mediation because it does not require the normality assumption to be met, and because it can be effectively utilized with smaller sample sizes. However, mediation continues to be most frequently determined using the logic of Barron and Kenny or the Sobel test. It is becoming increasingly more difficult to publish tests of mediation based purely on the Barron and Kenny method or tests that make distributional assumptions such as the Sobel test. Thus, it is important to consider your options when choosing which test to conduct. Approaches to mediation. While the concept of mediation as defined within psychology is theoretically appealing, the methods used to study mediation empirically have been challenged by statisticians and epidemiologists and interpreted formally. 1. Experimental causal chain design. An experimental causal chain design is used when the proposed mediator is experimentally manipulated. Such a design implies that one manipulates some controlled third variable that they have reason to believe could be the underlying mechanism of a given relationship. 2. Measurement of mediation design. A measurement of mediation design can be conceptualized as a statistical approach. Such a design implies that one measures the proposed intervening variable and then uses statistical analyses to establish mediation. This approach does not involve manipulation of the hypothesized mediating variable, but only involves measurement. See Spencer al. 2005 for a discussion on the approaches mentioned above. Criticisms of mediation measurement. Experimental approaches to mediation must be carried out with caution. First, it is important to have strong theoretical support for the exploratory investigation of a potential mediating variable. A criticism of a mediation approach rests on the ability to manipulate and measure a mediating variable. Thus, one must be able to manipulate the proposed mediator in an acceptable and ethical fashion. As such, one must be able to measure the intervening process without interfering with the outcome. The mediator must also be able to establish construct validity of manipulation. One of the most common criticisms of the measurement of mediation approach is that it is ultimately a correlational design. Consequently, it is possible that some other third variable, independent from the proposed mediator, could be responsible for the proposed effect. However, researchers have worked hard to provide counter-evidence to this disparagement. Specifically, the following counter-arguments have been put forward. 1. Temporal precedence. For example, if the independent variable precedes the dependent variable in time, this would provide evidence suggesting a directional, and potentially causal, link from the independent variable to the dependent variable. 2. Non-spuriousness and/or no confounds. For example, should one identify other third variables and prove that they do not alter the relationship between the independent variable and the dependent variable, he/she would have a stronger argument for their mediation effect. See other third variables below. Mediation can be an extremely useful and powerful statistical test, however it must be used properly. It is important that the measures used to assess the mediator and the dependent variable are theoretically distinct and that the independent variable and mediator cannot interact. Should there be an interaction between the independent variable and the mediator, one would have grounds to investigate moderation. Other third variables. 1. Confounding. Another model that is often tested is one in which competing variables in the model are alternative potential mediators or an unmeasured cause of the dependent variable. An additional variable in a causal model may obscure or confound the relationship between the independent and dependent variables. Potential confounders are variables that may have a causal impact on both the independent variable and dependent variable. They include common sources of measurement error as well as other influences shared by both the independent and dependent variables. In experimental studies, there is a special concern about aspects of the experimental manipulation or setting that may account for study effects, rather than the motivating theoretical factor. Any of these problems may produce spurious relationships between the independent and dependent variables as measured. Ignoring a confounding variable may bias empirical estimates of the causal effect of the independent variable. 2. Suppression. Suppression variables increase the predictive validity of another variable by its inclusion into a regression equation. For example, higher intelligence scores cause a decrease in errors made at work on an assembly line. However, an increase in intelligence could cause an increase in errors made on an assembly line, as it may also relate to an increase in boredom while at work, thereby introducing an element of carelessness resulting in a higher percentage of errors made on the job. Such a suppressor variable will lead to an increase in magnitude of the relationship between two variables. In general, the omission of suppressors or confounders will lead to either an underestimation or an overestimation of the effect of X on Y, thereby either reducing or artificially inflating the magnitude of a relationship between two variables. 3. Moderators. Other important third variables are moderators. Moderators are variables that can make the relationship between two variables either stronger or weaker. Such variables further characterize interactions in regression by affecting the direction and/or strength of the relationship between X and Y. A moderating relationship can be thought of as an interaction. It occurs when the relationship between variables A and B depends on the level of CC moderation. For further discussion, mediator variable. A mediator variable in statistics is a variable that describes how, rather than when, effects will occur by accounting for the relationship between the independent and dependent variables. A mediating relationship is one in which the path relating A to C is mediated by a third variable. For example, a mediating variable explains the actual relationship between the following variables. Most people will agree that older drivers are better drivers. Thus, aging better driving, but what is missing from this relationship is a mediating variable that is actually causing the improvement in driving experience. The mediated relationship would look like the following: aging increased experience driving a car better driving. Mediating variables are often contrasted with moderating variables, which pinpoint the conditions under which an independent variable exerts its effects on a dependent variable. Moderated mediation. Mediation and moderation can co-occur in statistical models. It is possible to mediate moderation and moderate mediation. Moderated mediation is when the effect of the treatment A on the mediator and/or the partial effect B on the dependent variable depend in turn on levels of another variable. Essentially, in moderated mediation, mediation is first established, and then one investigates if the mediation effect that describes the relationship between the independent variable and dependent variable is moderated by different levels of another variable. This definition has been outlined by Muller, Judd, and Iserbyt, Preacher, Rucker, and Hayes. Models of moderated mediation. There are 5 possible models of moderated mediation, as illustrated in the diagrams below. In the first model, the independent variable also moderates the relationship between the mediator and the dependent variable. The second possible model of moderated mediation involves a new variable which moderates the relationship between the independent variable and the mediator. The third model of moderated mediation involves a new moderator variable which moderates the relationship between the mediator and the dependent variable. Moderated mediation can also occur when one moderating variable affects both the relationship between the independent variable and the mediator and the relationship between the mediator and the dependent variable. The fifth and final possible model of moderated mediation involves 2 new moderator variables, one moderating the A path and the other moderating the B path. Mediated moderation. Mediated moderation is a variant of both moderation and mediation. This is where there is initially overall moderation and the direct effect of the moderator variable on the outcome is mediated. The main difference between mediated moderation and moderated mediation is that for the former there is initial moderation and this effect is mediated, and for the latter there is no moderation but the effect of either the treatment on the mediator is moderated or the effect of the mediator on the outcome is moderated. In order to establish mediated moderation, one must first establish moderation, meaning that the direction and/or the strength of the relationship between the independent and dependent variables differs depending on the level of a third variable. Researchers next look for the presence of mediated moderation when they have a theoretical reason to believe that there is a fourth variable that acts as the mechanism or process that causes the relationship between the independent variable and the moderator, or between the moderator and the dependent variable. Example: the following is a published example of mediated moderation in psychological research. Participants were presented with an initial stimulus that made them think of morality or made them think of might. They then participated in the CWRU unregistered trademark dilemma game, in which participants pretend that they and their partner in crime have been arrested, and they must decide whether to remain loyal to their partner or to compete with their partner and cooperate with the authorities. The researchers found that prosocial individuals were affected by the morality and might primes, whereas proself individuals were not. Thus, social value orientation moderated the relationship between the prime and the behavior chosen in the PDG. The researchers next looked for the presence of a mediated moderation effect. Regression analyses revealed that the type of prime mediated the moderating relationship of participants CWRU unregistered trademark social value orientation on PDG behavior. Prosocial participants who experienced the morality prime expected their partner to cooperate with them, so they chose to cooperate themselves. Prosocial participants who experienced the might prime expected their partner to compete with them, which made them more likely to compete with their partner and cooperate with the authorities. In contrast, participants with a pro-self social value orientation always acted competitively. Regression equations for moderated mediation and mediated moderation, Muller, Judd, and Iserbit outline three fundamental models that underlie both moderated mediation and mediated moderation. Mo represents the moderator variable, S, Mi represents the mediator variable, S, and I represents the measurement error of each regression equation. Step 1. Moderation of the relationship between the independent variable and the dependent variable, also called the overall treatment effect. To establish overall moderation, the I-43 regression weight must be significant. Establishing moderated mediation requires that there be no moderation effect, so the I-43 regression weight must not be significant. Step 2. Moderation of the relationship between the independent variable and the mediator. If the I-53 regression weight is significant, the moderator affects the relationship between the independent variable and the mediator. Step 3. Moderation of both the relationship between the independent and dependent variables and the relationship between the mediator and the dependent variable. If both I-53 in Step 2 and I-63 in Step 3 are significant, the moderator affects the relationship between the independent variable and the mediator. If both I-53 in Step 2 and I-65 in Step 3 are significant, the moderator affects the relationship between the mediator and the dependent variable. Either or both of the conditions above may be true. Causal mediation analysis, fixing versus conditioning. Although mediation is a causal notion, the bulk of mediation analysis has been conducted within the confines of linear regression which, unless strong conditions are met, is purely descriptive. Major developments in the 1990s gave rise to a new paradigm, based on causal diagrams and on counterfactual logic, which gives mediation a causal interpretation and extends the analysis from linear to nonlinear and non-parametric models. The premises of the causal approach is that it is not always appropriate to control for the mediator M when we seek to estimate the direct effect of X on Y. The classical rationale for controlling for M is that, if we succeed in preventing M from changing, then whatever changes we measure in y are attributable solely to variations in x, and we are justified then in proclaiming the effect observed as direct effect of x on y. Unfortunately, controlling for m does not physically prevent m from changing. It merely narrows the analyst's attention to cases of equal m values. Moreover, the language of probability theory does not possess the notation to express the idea of preventing m from changing, or physically holding m constant. The only operator probability provides is conditioning, which is what we do when we control for m, or add m as a regressor in the equation for y. The result is that, instead of physically holding m constant and comparing y for units under x equals 1 to those under x equals 0, we allow m to vary but ignore all units except those in which m achieves the value m equals m. These two operations are fundamentally different, and yield different results, except in the case of no omitted variables. To illustrate, assume that the error terms of m and y are correlated. Under such conditions, the structural coefficient b and a can no longer be estimated by regressing y on x and m. In fact, the regression slopes may both be non-zero even when c is 0. This has two consequences. First, new strategies must be devised for estimating the structural coefficients a, b and c. Second, the basic definitions of direct and indirect effects must go beyond regression analysis, and should invoke an operation that mimics fixing m, rather than conditioning on m. Definitions: such an operator, denoted do, m equals m, was defined in Perl and it operates by removing the equation of m and replacing it by a constant m. For example, if the basic mediation model consists of the equations, then after applying the operator do, m equals m, the model becomes where the functions f and g, as well as the distributions of the error terms i-1 and i-3 remain unaltered. If we further rename the variable y resulting from this operation as y, x, m, and, similarly, rename the variables m and y resulting from do, x equals x, as m, x, and y, x, respectively, we obtain what came to be known as potential outcomes, or structural counterfactuals. These new variables provide convenient notation for defining direct and indirect effects. In particular, 4 types of effects have been defined for the transition from x equals 0 to x equals 1, a, total effect, b, controlled direct effect, c, natural direct effect, d, natural indirect effect, where e stands for expectation taken over the error terms. These effects have the following interpretations: TE measures the expected increase in the outcome y as x changes from x equals 0 to x equals 1, while the mediator is allowed to track the change in x as dictated by the function m equals g, x, i-2. CDE measures the expected increase in the outcome y as x changes from x equals 0 to x equals 1, while the mediator is fixed at a pre-specified level m equals m uniformly over the entire population. NDE measures the expected increase in y as x changes from x equals 0 to x equals 1, while setting the mediator variable to whatever value it would have obtained under x equals 0, that is, before the change. NIE measures the expected increase in y when the x is held constant, at x equals 0, and m changes to whatever value it would have attained under x equals 1. The difference TE and DE measures the extent to which mediation is necessary for explaining the effect, while the NIE measures the extent to which mediation is sufficient for sustaining it. A controlled version of the indirect effect does not exist because there is no way of disabling the direct effect by fixing a variable to a constant. According to these definitions, the total effect can be decomposed as a sum, where NIA stands for the reverse transition, from x equals 1 to x equals 0. It becomes additive in linear systems, where reversal of transitions entails sign reversal. The power of these definitions lies in their generality. They are applicable to models with arbitrary nonlinear interactions, arbitrary dependencies among the disturbances, and both continuous and categorical variables. The mediation formula: in linear analysis, all effects are determined by sums of products of structural coefficients, giving. Therefore, all effects are estimable whenever the model is identified. In nonlinear systems, more stringent conditions are needed for estimating the direct and indirect effects. For example, if no confounding exists, the following formulas can be derived. The last two equations are called mediation formulas and have become the target of estimation in many studies of mediation. They give distribution-free expressions for direct and indirect effects and demonstrate that, despite the arbitrary nature of the error distributions and the functions f, g, and h, mediated effects can nevertheless be estimated from data using regression. The analyses of moderated mediation and mediating moderators fall as special cases of the causal mediation analysis, and the mediation formulas identify how various interactions coefficients contribute to the necessary and sufficient components of mediation. Example: assume the model takes the form where the parameter quantifies the degree to which M modifies the effect of X on Y. Even when all parameters are estimated from data, it is still not obvious what combinations of parameters measure the direct and indirect effect of X on Y, or, more practically, how to assess the fraction of the total effect that is explained by mediation and the fraction of that is owed to mediation. In linear analysis, the former fraction is captured by the product, the latter by the difference, and the two quantities coincide. In the presence of interaction, however, each fraction demands a separate analysis, as dictated by the mediation formula, which yields. Thus, the fraction of output response for which mediation would be sufficient is, while the fraction for which mediation would be necessary is. These fractions involve non-obvious combinations of the model's parameters, and can be constructed mechanically with the help of the mediation formula. Significantly, due to interaction, a direct effect can be sustained even when the parameter vanishes and, moreover, a total effect can be sustained even when both the direct and indirect effects vanish. This illustrates that estimating parameters in isolation tells us little about the effect of mediation and, more generally, mediation and moderation are intertwined and cannot be assessed separately. Statistical relationships. There are several relationships defined in statistical analysis as follows: direct relationship, mediating relationship, moderating relationship, spurious relationship. References. As of June 19, 2014, this article is derived in whole or in part from causal analysis in theory and practice. The copyright holder has licensed the content utilized under CC by SA and GFDL. All relevant terms must be followed. Notes. Bibliography: Preacher, Christopher J. Hayes, Andrew F. SPSS and SAS Procedures for Estimating Indirect Effects in Simple Mediation Models. Behavior Research Methods, Instruments, and Computers 36, 717 €731 doi, 10.3758/BF03206553. Preacher, Christopher J. Hayes, Andrew F. Asymptotic and Resampling Strategies for Assessing and Comparing Indirect Effects in Multiple Mediator Models. Behavior Research Methods 40, 879 €891 doi, 10.3758/BRM. 40.3.879. PMIDA 18,697,684. Preacher, K.J. Ziffer, M.J. Zhang, Z.A. General Multi-Level SEM Framework for Assessing Multi-Level Mediation. Psychological Methods 15, 209 €233 doi, 10.1037 per R0020141. PMIDA 20,822,249. Barron, R.M. and Kenny, D.A. The Moderator-Mediator Variable Distinction in Social Psychological Research. Conceptual, Strategic, and Statistical Considerations, Journal of Personality and Social Psychology, Volume 51, 6, pp. 1173–1182. Cohen, J. Statistical Power Analysis for the Behavioral Sciences. New York, New York, Academic Press. Hayes, A.F. Beyond Barron and Kenny, Statistical Mediation Analysis in the New Millennium. Communication Monograph 76, 480 euro 420 doi, 10.1080/03637750903310360 Howell, D.C. Statistical Methods for Psychology. Belmont, C.A., Cengage Learning. McKinnon, D.P. Lockwood, C.M. Advances in Statistical Methods for Substance Abuse Prevention Research. Prevention Science 4, 155 euro 171 doi, 10.1023 per hour, 1,024,649,822,872. PMCA 2,843,515. PMIDA 12,940,467. Preacher, K.J. Kelly, K. Effect Sizes Measures for Mediation Models, Quantitative Strategies for Communicating Indirect Effects. Psychological Methods 16, 93 euro 115 doi, 10.1037 per hour 00222658. PMIDA 21,500,915. Rucker, D.D., Preacher, K.J., Tormala, Z.L. and Petty, R.E. Mediation Analysis and Social Psychology, Current Practices and New Recommendations. Social and Personality Psychology Compass, 5/6, 359-371. Sobel, M.E. Asymptotic Confidence Intervals for Indirect Effects in Structural Equation Models. Sociological Methodology 13, 290 euro 312 doi, 10.2307/270723. Spencer, S.J. Zanner, M.P. Fong, G.T. Establishing a Causal Chain, Why Experiments Are Often More Effective Than Meditational Analyses in Examining Psychological Processes. Attitudes and Social Cognition 89, 845 euro 851 doi, 10.1037/0022-3514.89.6.845. Pearl, Judea. The Mediation Formula, A Guide to the Assessment of Causal Pathways in Nonlinear Models. In Biziani, C. DeWood, P. Bernardinelli, L. Causality, Statistical Perspectives and Applications. Chichester, UK, John Wiley & Sons, Limited PPA 151 euro 179. External links, Summary of Mediation Methods at PsychWiki, Example of Causal Mediation Using Propensity Scores. The Methodology Center, Penn State University, Book on Moderation and Mediation Analysis, including an introduction to the process macro for SPSS and SAS. Andrew F. Hayes, Ohio State University. In statistics, a mediation model is one that seeks to identify and explicate the mechanism or process that underlies an observed relationship between an independent variable and a dependent variable via the inclusion of a third explanatory variable, known as a mediator variable. Rather than hypothesizing a direct causal relationship between the independent variable and a dependent variable, a mediational model hypothesizes that the independent variable influences the mediator variable, which in turn influences the dependent variable. Thus, the mediator variable serves to clarify the nature of the relationship between the independent and dependent variables. In other words, mediating relationships occur when a third variable plays an important role in governing the relationship between the other two variables. Researchers are now focusing their studies on better understanding known findings. Mediation analyses are employed to understand a known relationship by exploring the underlying mechanism or process by which one variable influences another variable through a mediator. For example, suppose a cause X affects a variable presumably through some intermediate process. In other words, X leads to M leads to Y. Thus, if gender is thought to be the cause of some characteristic, one assumes that other social or biological mechanisms associated with gender can explain how gender-associated differences arise. Such an intervening variable is called a mediator. Barron and Kenny's steps for mediation. Barron and Kenny laid out several requirements that must be met to form a true mediation relationship. They are outlined below using a real-world example. See the diagram above for a visual representation of the overall mediating relationship to be explained. Step 1. Regress the dependent variable on the independent variable. In other words, confirm that the independent variable is a significant predictor of the dependent variable. Independent variable dependent variable. Note, if step 1 does not yield a significant result, one may still have grounds to move to step 2. Sometimes there is actually a significant relationship between independent and dependent variables, but because of small sample sizes, or other extraneous factors, there could not be enough power to predict the effect that actually exists. Direct versus indirect mediation effects. In the diagram shown above, the indirect effect is the product of path coefficients A and B. The direct effect is the coefficient C. The direct effect measures the extent to which the dependent variable changes when the independent variable increases by 1 unit. In contrast, the indirect effect measures the extent to which the dependent variable changes when the independent variable is held fixed and the mediator variable changes by the amount it would have changed had the independent variable increased by 1 unit. In linear systems, the total effect is equal to the sum I squared 11 is significant. Step 2, regress the mediator on the independent variable. In other words, confirm that the independent variable is a significant predictor of the mediator. If the mediator is not associated with the independent variable, then it could unregistered trademark T possibly mediate anything. Independent variable mediator. I squared 21 is significant. Step 3, regress the dependent variable on both the mediator and independent variable. In other words, confirm that the mediator is a significant predictor of the dependent variable, while controlling for the independent variable. This step involves demonstrating that when the mediator and the independent variable are used simultaneously to predict the dependent variable, the previously significant path between the independent and dependent variable is now greatly reduced, if not non-significant. I squared 32 is significant. I squared 31 should be smaller in absolute value than the original mediation effect. Example: the following example, drawn from Howell, explains each step of Barron and Kenya unregistered trademark S requirements to understand further how a mediation effect is characterized. Step 1 and Step 2 use simple regression analysis, whereas Step 3 uses multiple regression analyses. Step 1. How you are parented predicts how confident you feel about parenting your own children. How you are parented confidence in own parenting abilities. Step 2. How you are parented predicts your feelings of competence and self-esteem. How you are parented feelings of competence and self-esteem. Step 3. Your feelings of competence and self-esteem predict how confident you feel about parenting your own children, while controlling for how you are parented. Such findings would lead to the conclusion implying that your feelings of competence and self-esteem mediate the relationship between how you are parented and how confident you feel about parenting your own children.